Hello everyone, this is VPCB, your trusted PCB partner. Today, our topic is the advantages, disadvantages, and selection of 4-layer board stack-up orders, part 2. In the previous episode, we already introduced that B has 3 types of stack-up structures. We have already covered the first stack-up structure, which is solution 1 here, and discussed its pros and cons. Today, we will continue to introduce the remaining 2. Solution 2 is as follows. We can see that the top layer is signal, the second layer is GND, the third layer is power, and the fourth layer is signal again. This is the stack-up structure that we previously recommended for 4-layer boards and is also a commonly used and versatile option. The advantage of this structure is its excellent signal integrity. The first signal layer S1 is adjacent to GND and S2 is adjacent to the power layer. So we see that S1 is next to GND and S2 is next to the power layer. This provides an excellent controlled impedance transmission line structure with a clear and low impedance signal return path, low parasitic capacitance, and optimal power integrity. The GND and power planes are closely connected, forming a large planar capacitance that provides extremely low power impedance. The power distribution network is very stable, making it suitable for high-speed and high-power applications. This is also the most commonly used and recommended 4-layer board stack-up structure. This structure is most widely used in high-speed digital circuits and RF circuits, offering the most balanced performance. The drawback is, first of all, in terms of EMI. With the signal layers on the outer layers, the direct shielding effect against EMI is not as good as when the outer layers are ground planes. When high-speed signals are on the outer layers, electromagnetic radiation can spread into the surrounding space, which may require additional external shielding. In terms of power supply impedance, it is not easy to maintain low power impedance. This actually refers to the thickness of the dielectric. If the dielectric between L2 and L3 is too thick, it will indeed increase the power impedance. However, by choosing thin dielectric materials such as 0.1 millimeters or even thinner, the GND and power planes can be made very close together, thereby achieving extremely low power impedance. This is about the middle layer. The thickness of the core layer's dielectric will affect the power impedance. If it is relatively thick, then the power impedance will be correspondingly higher. Next, the explanation is actually quite clear and straightforward. Since the signals are positioned on the very outside, both the external radiation they receive from their surroundings and the radiation they emit outward into the environment are not easily controlled or managed effectively. However, when it comes to layout, you can see that the signals on both sides, whether routed on the top layer or the bottom layer, can be directly spread outward without the need for vias. So this layout is also very advantageous. Therefore, this is the most recommended type of layout. And the applicable scenarios are most high-speed, high-density digital circuits. For example, computer motherboards, mobile phones, and communication equipment basically all use this type of layout. Next, let's look at the third scheme. The first layer uses GND, the 2 middle layers are signal layers S1 and S2, and the bottom layer is the power layer. The difference from the first scheme is that the power layer is placed separately on the bottom layer. As for this scheme, its advantage is still relatively good EMI shielding, which is quite similar to the first case. The outer layers are ground planes, providing excellent EMI shielding. Also, the signal quality of S1 is exceptionally good and highly reliable because the L2 signal, which specifically means the S1 signal layer, is positioned directly adjacent to the L1 layer. This precise placement ensures that it is immediately next to the ground plane, thereby contributing to its excellent signal integrity and overall performance. The signal quality can be well ensured, so routing high-speed signals or those requiring impedance control on this layer will yield better results. The significant downside to this particular design approach is the inherently poor power integrity that results primarily because the dedicated power plane situated on layer L4 and the corresponding GND plane located on layer L1 are physically separated and positioned quite far apart from each other within the PCB stackup. As mentioned earlier, the large distance between the two increases resistance, which leads to higher power impedance and poorer power integrity, making it unsuitable for applications that require high power stability. Also, the signal quality of S2 may be affected as the nearest ground plane to the S2 signal is relatively far away since there is a layer in between. The signal return path may not be as ideal as in the second scenario. It's not as good as the second option. This configuration is suitable in scenarios where EMI requirements are strict but the internal signal rates are relatively low. If the board itself has strong resistance to interference sources, it can be considered, but you need to accept the compromise in power integrity. Actually, this has the same problem as the first one. Whether you're laying out components on the top or bottom layer, you have to use vias or blind vias to route the traces out before you can start wiring. Next, in actual design, the second scenario, meaning the second solution, is usually the best general purpose 4-layer stack-up scheme. It achieves the optimal balance among signal integrity, power integrity, and EMI control. Although having signal layers on the outer layers may slightly increase EMI risk, this can be effectively managed through good routing practices such as controlling signal loop areas and effective management. Alright, that concludes our discussion on the pros and cons of 4-layer PCB stack-up orders and how to choose among them. If you enjoyed this video, please subscribe to my channel for more content. Thank you, everyone.